Hey guys, welcome to this next video lecture on input-output organization. Till now we have talked about three type of categorizations of input-output. We have already talked about the memory mapped versus isolated I/O. We have talked about synchronous versus asynchronous I/O. We have talked about serial versus parallel I/O. One thing that we also talked about was that these categorizations were mutually independent, which means that you can have a memory mapped serial asynchronous I/O as well as a memory mapped parallel synchronous I/O and so on. That brings us to the last categorization of input output, that is the program controlled I/O versus interrupt driven I/O versus direct memory access, that is also called the DMA. Now, before we go into the nuances of the details of all these three types of input output, let's first understand the basis on which these three categorizations have been formed. See, we normally talked about the transfer of data between the CPU and the input output devices. But in actuality, the source or the destination of the data that is being transferred between the input output devices and the CPU is actually the memory. See, if I'm talking about data input, the CPU is reading some data from the input device, but where is the data going? The data is actually going into some variable in the memory. Similarly, if I'm talking about the output device, output operation, the CPU is sending certain data to the output device. But where does this data originate? This data once again originates at some location, some variable in the memory. So what I want to say is that all the input output operations that are being performed between the data transfer that is being done between the CPU and the input output devices, the actual source and the actual destination of the data is the memory unit. What the CPU does, the CPU is simply a way of executing the input output instructions. Input output instructions, we are familiar with printf, scanf. These are the puts, gets. These are the instructions. Get ch, put char, get char. If I'm talking about, let us say, C. If I'm talking about, let us say, C++, there will be C in, C out and things like that. So these are the instructions which are, when encountered by the CPU starts a input output cycle, right? So the CPU is just a medium, just a way of executing these input output instructions to facilitate the data transfer from the input device or to the output device. Now, this data transfer that I'm talking about that happens between the CPU and the input output device, in actuality the input output device and the memory unit through the CPU. Now, this can happen in a number of ways. The different ways actually depend on the level of involvement of the CPU. Some of these operations may require the CPU to be totally committed, so that the CPU is involved in each and every piece of data that is being transferred from the IO device to the memory device. There may be some other cases, some other ways of IO where the involvement of the CPU is not as much, right? Let's talk about these. Let's first begin with program controlled input output. Now, what the program controlled input output essentially means, that program controlled input output is performed in response of input output instructions that are encountered by the CPU in your program. So each and every data item that is transferred to the output device or from the input device, that is done with the full cooperation, full involvement of the CPU, right? So the IO device does not have the direct access to the memory. Whatever data transfer is being happening, whatever data transfer has to take place, whether it has to go from memory to output or input to memory, it has to go through the CPU. As you can see over here, this is the flowchart for the entire programmed IO. Now, when I say enter, it means the CPU enters this flowchart as soon as it encounters a input output instruction. Now, please see this flowchart very carefully. There are two loops in this flowchart, right? Now, as the CPU enters this cycle, whenever the CPU encounters an input or output instruction, let us assume that the CPU is going to read some data off the disk and store it in the memory. Let's take a simple example. Now, as the CPU enters this particular cycle, The first thing it has to do, it has to check the status of the disk. Now CPU cannot read any data from the disk unless the disk is ready. Now when I say the disk is ready, please understand, before the CPU can read the data of the disk has to start rotating, the disk has to attain a particular speed, then the read write head has to be positioned over the appropriate track and the sector before the actual data transfer can take place. So now the CPU, first of all, what does it do? It checks the status of the disk. Now this is a repetitive process. See, what happens is, as soon as the CPU enters into the cycle, it starts asking the disk, are you ready? Are you ready? Are you ready? Are you ready? Now this goes on till the time the disk responds, yes, I am ready. So this first loop that you can see over here, or the inner loop that you can see over here, is executed as many times as is required before the disk actually becomes ready to transfer the data. Right? Now, let us assume that disk is now ready, or the device, whatever we are talking about, let us say the input device or the output device, whatever device we are talking about, it is now ready for the data transfer. Right? Now what happens is, now one piece of data, it can be a byte of data, it can be a word of data, it can be a record of data, it can be a sector of data. One piece of data is transferred from the input device to the memory, or from the memory to the output device. Just one piece of data. Once that one piece of data has been transferred, now the CPU once again checks whether the input output process has been completed. What I mean is, are all the pieces of information that were required have been transferred? If they are, it comes out of the input output cycle. If not, it goes back to the starting point. Now, as I started off, there are two loops over here. One is the inner loop, one is the outer loop. The inner loop checks for the readiness of the device. The outer loop is executed as many times as there are data items. Right? So the CPU is stuck in these two loops until the entire set of data is read. Now say, for example, if I want to transfer 1,000 pieces of data. Now for the 1,000 pieces of data, this outer loop will be executed 1,000 times. This inner loop may be executed, let us say 1,000 times or 10,000 times or million times for each data item. Why? Because the speed at which the CPU transfers the data is quite high. It is very fast as compared to the rate at which the device becomes ready to give or take the next piece of information. So this programmed IO, also called the polled IO, is quite wasteful of the CPU time. Next, let's come to interrupt driven IO, or interrupt initiated IO. Now, as we said, that there were two loops. One was the inner loop, which was checking the readiness of the device, and one was the outer loop, which was the number of times that the data was, that entire process was being repeated, which depended on how many data items were to be transferred. Right? Now, this particular method of transfer, interrupt initiated IO, what it does, it now puts the responsibility of status checking of the device to the device itself. Now, instead of CPU repeating the query, are you ready, 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 and so on, numerous number of times, now what does the CPU do? It simply tells the device that I want to perform a communication. Whenever you are ready, you come and tell me. So this, once the CPU knows that it needs to transfer some piece of data, whether it wants to read some data or it wants to write some data. So what CPU does, it simply tells the IO device that, okay, I want to perform a data transfer. Whenever you are ready, you come and tell me. Now, how does the device intimate the CPU about this? It is done with the help of an interrupt. Now, an interrupt is a signal that tells the CPU that something or someone wants its attention. Say, for example, if I'm taking a class, you raise your hand. This is a signal for me that you want my attention. So I have to solve your query. I have to perform a particular operation to whatever interruption is there. Similarly, whenever the device is ready to accept the data or give the data, what the device does, it simply gives the signal to the CPU. Now, this is the process over here. Once again, whenever the CPU encounters a particular operation, particular input output instruction, sorry, it enters this particular cycle, it issues the read or write request to the disk. And then instead of again and again checking the readiness of the disk, what it does, it goes on processing other tasks till the time that the disk or the whatever device we are talking about becomes ready. Now, whenever the device becomes ready, it issues an interrupt. It issues an interrupt, and that interrupt, when it is noticed by the CPU, what does the CPU do? The CPU stops whatever it is doing. It might be after the immediate instruction or it might be after the immediate task. Now the CPU stops whatever it is doing and then performs the operation that is required by the device. It can be an input-output operation or it can be an output operation. Now this is done once. The outer loop, which was executed as many times as there were number of elements, is still the same, right? Now there interrupts. Let's spend a little time on interrupts. What is an interrupt? As I said earlier, an interrupt is any signal that tells the CPU that yes, I want your attention. Now the interrupts can once again be categorized in three ways depending upon their source, depending upon their priority, and depending upon their routine. Now let us first understand how an interrupt is handled. See, whenever an interrupt occurs, a signal is sent to the CPU. Now, whenever an interrupt is occurring, the CPU comes to know of the interrupt. How does the CPU react? The CPU reacts by executing a special program. This program is called the Interrupt Service Routine, the ISR. This is a special code that is written, that is stored somewhere in the control memory, and there is a separate ISR for each and every type of interrupt. Right, let's first understand what are the various types of interrupts. On the basis of source, we have two types of interrupts. One is the hardware interrupt and one is the software interrupt. A hardware interrupt is one which is originated in the hardware. Say for example, your disk drive may be issuing an interrupt, your printer may be issuing an interrupt telling the CPU that I am out of paper. The printer may be telling the CPU I am out of toner. Your CD drive may be telling the CPU that I don't have a CD. You are trying to click on the CD drive, but there is no CD. So whatever interrupts are generated by the hardware devices, they are called the hardware interrupts. On the other hand, software interrupts are initiated by instructions in the CPU. You may have an instruction which is causing, let us say, that divide by zero error. Now to handle that divide by zero error, whenever the divide by zero error occurs, the software sends an interrupt to the CPU telling ki boss, I cannot go any further because there is a divide by zero error. Or you may yourself use a special instruction to call an interrupt. On the basis of priority, we have maskable versus non-maskable interrupt. Let's take a very simple example. Say for example, let us say I'm taking a class and my phone rings. Now I go and see who is ringing me up. Now there are two possibilities. The first, I'm getting a call from, let us say, some of my friends which I can ignore for the duration of my class. So what do? I just silent the phone or I cut that call and I wait for the class to be over and then I return back the call. The second is, I may be getting a call which cannot be ignored. Let us say a call from VC sir, or let us say some other important call. Then what I do is I finish that particular sentence that I'm speaking and then I say excuse me and then I take the call. Similarly, there are two types of interrupts, maskable versus non-maskable interrupts. In case of a maskable interrupt, the CPU executes the current task and then stops and goes on to execute the ISR. And in case of a non-maskable interrupt, the CPU stops after the current instruction to execute the ISR. Now, as I stated earlier, that each and every ISR is stored somewhere in the control memory. Now, before a CPU can start executing the ISR, it has to locate the ISR. Now, how does the CPU locate the ISR? Once again, there are two ways. In case of a vectored interrupt, the interrupt, whatever device is causing or whatever instruction is causing an interrupt, sends the information about the location of the interrupt service routine to the CPU. In case of a non-vectored interrupt, the CPU uses something that is called as a interrupt table. That interrupt table has the information about the ISRs of all the interrupts. So the CPU goes directly to the interrupt table and looks up the interrupt that has caused it to suspend the operation, and then locates and executes the given interrupt. So this is the process of the handling of interrupt. What does the CPU do? Whenever an interrupt is encountered, what does the CPU do? It disables further interrupts temporarily. It saves the processor status. Now, whenever the CPU is saving the processor state or restoring the processor state, it needs to disable further interrupts. Now, why do we need to save or restore the processor status? Because executing the ISR is exactly similar as running a subroutine or as calling a function. Before we jump onto a subroutine, before we jump onto a function call, we need to save the system process status. So it saves the processor status, enables further interrupts, determines the cause of interrupt, services the interrupt, then again it disables the interrupt, restores processor status, again enables further interrupts, and then returns from interrupts. Third, now we have more or less eliminated the inner loop. Now let's talk about the outer loop. Say for example, I have to transfer 1,000,000 pieces of data between the input device and between the IO device and the memory. Essentially, the CPU is doing nothing, but it is providing a sort of a railway junction. The data is transferring from one point to another, just passing through the CPU. It is not performing any useful task for me. So what I can do is I can bypass the CPU completely by using direct memory access. But it does not mean that I do not need any processor for that. For performing DMA, I need a special type of a processor which is called a DMA controller. Now, the process happens something like this. Whenever a bulk transfer has to occur, the CPU, when it gets a bulk transfer request, wakes up the DMA controller, tells it, okay boss, now it is time for you to start working. Now I want you to perform an transfer operation. This is the memory location from where the transfer has to be done. This is the number of words that you have to transfer. And third thing, this is a read operation or a write operation. And once these three things have been told to the DMA controller, now the CPU is free to perform other tasks. Now it becomes the responsibility of the DMA controller to perform the task. The actual task is performed by the DMA controller. See, the DMA controller, as you can see over here, in the other modes of transfer, the pathway is between IO to CPU to memory or memory to CPU to output device. But here the transfer is between the IO device and the memory device directly or memory to IO device directly. Now, if the DMA controller has to transfer bulk data between the IO device and the memory, it will perform this using the bus. But there is a single bus. Either the CPU can use it or the DMA controller can use it. So what happens is the DMA controller has to request the CPU for the control of the bus. This is done with the help of a DMA request. Then as soon as the CPU can relinquish the control of the bus, it tells the DMA controller by sending a DMA acknowledge. And then the DMA controller performs the data transfer between the memory and the device. So this is the entire process. CPU sets up the disk for DMA transfer. DMA device begins transfer independent of the CPU. Now, once the DMA has finished the task, now there are once again two possibilities. Either the DMA has successfully completed the task or there was some problem. So in either of the cases, the DMA device then tells the CPU about the status of the operation by using an interrupt. Once again, we use a interrupt over here. So this is the typical DMA operation. So the typical DMA operation is the processor initiates the DMA controller by identifying the input output device, supplying the memory address, how many bytes have to be transferred, and the type of operation, whether it is an input out operation or a output operation. This is something that is called as channel initialization. Then the IO device, whenever the IO device is ready to transfer data, it simply informs the DMA controller. Then the DMA controller requests the CPU for the control of the bus. After getting the control of the bus, the DMA performs the input output transfer, and once that transfer is complete, the DMA intimates the CPU about this regarding the success or the failure of the operation by using an interrupt. So this was about the three modes of operations, right? Now, one term we have been using throughout the input output operations till now, that is the bus. In the next lecture, we will talk about the details of this bus, right? Till then, ciao.